Hey everybody, we're going to do some 3.06 notes. It has to do with connecting the free body diagrams to the motion of an object. So we can, if we have a little bit of information about the object and we also have the free body diagram, we can talk about whether something's speeding up, slowing down, constant speed, things like that. So the first thing you guys need to know about this, and I think we've talked about it a little bit, is that the net force, where are my drawing tabs? There we go. The net force of an object varies with its acceleration. And we know that from this equation that we've talked about a little bit. F equals, it's really F net. F net equals M, it's hard for me to draw on this, MA. Okay, so that means net force equals mass times acceleration. So through that, we're going to take a look at what happens if the acceleration is positive, what happens if it's negative, what happens if it's zero, and how that connects to F net. So let's get back to this. We're going to take a look at this rocket sled. So you can see that they have a free body diagram up here. There's some friction, but we turned off drag. So once he starts getting moving, you're going to see the friction pointing up, opposing his motion, because we know force of friction opposes the motion. So I'm going to move him this way. And you can see that I've got an applied force here of 100, a friction force of negative 50. They don't give you the weight, the force of gravity and the normal force numbers because they just balance out. He's not moving up and down. And what you can see is that the speed is moving up. He's accelerating. And we can connect that to the net force because the net force is positive. So he should be speeding up if his net force is positive. Well, if his net force is positive and his direction is positive. So he's moving to the right. So we've got a positive net force and we've got a positive direction. I'm going to slow him down a little bit. So to slow him down, all I have to do is change the direction of his net force. So now it's negative. It's pointing to the left. And he's going to the right, so you can see that his speed is slowing down. So if we have a net force that points to the left, like this does, because negative 50, that arrow is bigger than this positive 20 arrow, and he's moving to the right, then he's going to slow down. Now I'm going to even it out. And this is a balanced friction force and applied force. The net force is 0, and you can look at his speed, and his speed is staying the same. Sometimes people think that if we balance him out, he's going to stop, but he'll only stop once his net force opposes his motion. So again, if I go down here and I give him a net force of negative 30, he's slowing down, and if I let him go long enough, he'll eventually stop. Depending on how big the applied force is, if he can overcome force of friction, then he'll start going the opposite direction. So right now he's going this way. If he stops and he can overcome force of friction, he'll start going that way, but don't worry about that. So the big thing is if the object is slowing down, the net force will oppose the motion. If the object's speeding up, the net force will go with the motion. And if it's maintaining a constant speed, there's no net force. And that's all directly linked with the acceleration. Okay, F net equals ma. All right, we're going to move on and draw some free body diagrams.
It's now time to return to homerooms for advisory.
All right. So we've got this, we've got 3 free body diagrams that we need to draw. So we've got the object that's been thrown upwards and is in midair slowing down. So we know that if it's going up but slowing down, the net force needs to be pointing down. So I'm going to draw the first one there. All right, and that's going to be my FG. So force of gravity. The other force at play here is going to be drag, and since the object is moving upwards, my drag is pointing downwards. I don't really know what the force of the drag is going to be. I'll just draw it smaller, and I'll put F. And I usually would write out drag, but as you can see, it takes me a long time to write with this pencil. So this here, that's F drag. So what we should see, because it's going upwards, is the net force should be pointing downwards because it's slowing down, and it is. We have nothing pointing upwards, no force is pointing upwards. So the net force is down. The next one, an object's on a table, it's moving to the left at a constant speed. And that's kind of a trick because you actually don't even need to know which way it's moving because you know it's moving at a constant speed. So that way you know, hey, the net force is 0, so it doesn't even matter. So we're going to put force of gravity pointing down and normal force pointing up. And what you will find, these arrows should balance each other out. So I did my best to draw them about the same length. And then if we think about it, it doesn't say anything about an applied force. So this object that's on the table and moving to the left, it might be getting pushed. If it's getting pushed, then that applied force would balance out with the friction. It doesn't say anything about being pushed though. So think about if we had a marble on one of the lab tables or one of the tables in the classroom, there's very little, if not like really no friction between those two things. So think about that where it would be no one's pushing the marble across the table, but it just keeps going. It never stops. So that's a constant speed. Okay, the last one, an object's been thrown upwards and is moving downwards, speeding up. So here we go. We're going to start with force of gravity. That's always pointing down. If it's going downwards and it's speeding up, that means the net force has to be pointing in the direction of the object, which would be down. Also, if it's going downwards, drag would be pointing up. So in order for the net force to be, let me erase this a little bit. In order for the net force to be going down, I need to make sure that my arrow for force of gravity is bigger than my arrow for F drag. And I just want to make it like really abundantly clear. So this would be clearly the net force is pointing down. Clearly force of gravity is bigger than drag in this one. And again, I'm just going to write FD for drag. Okay, so here we have a net force pointing down, which makes sense because it's going down and speeding up. So, and by speeding up means getting faster, not speeding upwards. So it's getting faster going down. So that's where we should see the net force. It should be pointing down. All right.